So in this class we will discuss the Fourier transform. So the Fourier transform pair. Let us start with Fourier transform pair. So the Fourier transform pair is we have x omega, and that is equals to Fourier transform of xt, and it can be written as minus infinity to plus infinity xt e raised to the power minus j omega t into dt. And if we find out the inverse Fourier transform, that is if we find out xt from x omega, then it is simply the Fourier inverse of x omega, and that is equals to 1 divided by 2 pi minus infinity to plus infinity x omega e raised to the power j omega t into d omega. So it is simply xt is basically x omega, means this is basically that Fourier transform pair. So let us discuss the Fourier spectra. Let us discuss the Fourier spectra. So we have x omega, and that is equals to modulus of x omega e raised to the power j phi omega. So basically if xt is real, then what we are going to get? We are going to get that x minus omega is equals to x conjugate omega. So this is the first relation we are going to get, that x minus omega is equals to x conjugate omega when xt is real. So we make the following statement for real valued signal, that so we can make a statement related to real valued signal is that the amplitude, please understand, the amplitude spectrum of signal, of real valued signal, the amplitude spectrum of real valued signal is an even function of omega, is an even function of omega. Because if we take the modulus on both sides, then what we will get? We will get modulus of x minus omega is equals to x conjugate omega. So that amplitude spectrum for real valued signal is an even function of omega, and so basically we can say that the amplitude spectrum is symmetric with respect to the frequent origin. So also we can write that the amplitude spectrum is symmetric. The amplitude spectrum is symmetric with respect to origin omega. So it is basically symmetric. The second condition is that phi minus omega is minus of phi omega. So it means that the conclusion, very important conclusion, is that the phase spectrum of the signal, the phase spectrum of the signal is an odd function of frequency, is an odd function of is an odd function of frequency, is an odd function of frequency. So we can see that 5 minus omega is equal to minus 5 omega, that is odd. So it is basically the odd. Now let us discuss the convergence of Fourier transform. So convergence of Fourier transform. Convergence of Fourier transform. So the following conditions should satisfy. So there are like in Fourier series we have Dirichlet. We have Dirichlet conditions for convergence of Fourier series also. So we have Dirichlet conditions. So what are those conditions? Please understand that what are those conditions. So first condition is xt is absolutely integrable, that is minus infinity to plus infinity modulus of xt dt is less than infinite. Second condition is that xt has a finite number of finite number of maxima and minima. Xt has a finite number of maxima and minima within any finite interval. Within any finite interval. And the third condition is and also within an finite interval, and each of these discontinuities is finite, and each finite number of maxima and minima within a finite interval. So let us discuss the discontinuities also. So we can write this in separate lines. So if xt has a finite number, since xt has a finite number of discontinuities, maybe so that Dirichlet condition is saying that maybe xt is a discontinuous signal, but xt must be finite discontinuities. Xt must be finite number of discontinuities within any finite interval. Within any finite interval, and each of these discontinuities is finite, and each of these discontinuities is finite, and basically these are called the Dirichlet conditions. So next is the condition between the relation between the Fourier transform and Laplace transform we are going to discuss, and also the connection between the Laplace transform and Fourier transform. And also we will find out the condition on which the Laplace transform will converge to Fourier transform. We will find out this. So let us start the Fourier transform of a particular signal xt. So the Fourier transform, let us discuss this. The Fourier transform of signal xt is written as ex omega, and that is equals to minus infinity to plus infinity xt e raised to the power minus j omega t into dt. So this is the Fourier transform of signal ext, and the Laplace transform is written as, and the Laplace transform is given as xs, that is equals to minus infinity to plus infinity xt e raised to the power minus st into dt. So this is the Laplace transform. So the Fourier transform is specified basically this Fourier transform is basically the special case of Laplace transform when we consider that s is equals to j omega. So if we put s is equals to j omega, so what we will get? We will get x j omega, and that is equals to minus infinity to plus infinity xt e raised to the power minus j omega t into dt, and that is simply x omega we can get, right? So the Fourier transform, so basically the Fourier transform is a special case. So the Fourier transform is a special case of Laplace transform. The Fourier transform is a special case of Laplace transform in which s is equals to j omega, so that is we have xs, and when we have s is equals to j omega, and that is equals to Fourier transform of xt, that is equals to Fourier transform of xt. So setting s is equal to sigma plus j omega, what we can obtain, we have, so let us set s is equal to sigma plus j omega instead of j omega, only we are setting sigma plus j omega. So it is x sigma plus j omega is equals to minus infinity to plus infinity xt e raised to the power minus sigma plus j omega into t dt, and that sigma plus j omega, x sigma plus j omega is equals to minus infinity to plus infinity ext e raised to the power minus sigma t e raised to the power minus j omega t into dt, and that is equals to, so this x sigma plus j omega can be written as, please understand that, so this x sigma plus j omega is written as, thus simply it is written as the Fourier transform of xt e raised to the power minus sigma t, that is equals to Fourier transform of xt e raised to the power minus sigma t. So it indicates that, which indicates that the bilateral Laplace transform, the bilateral Laplace transform of xt, the bilateral Laplace transform of xt can be interpreted as the Fourier transform of ext e raised to the power minus sigma t, xt e raised to the power minus sigma t. So again we are going to discuss, since the Laplace transform may be considered a generalization of Fourier transform in which j omega is basically changes to s is equal to sigma plus j omega. So this j omega is basically changes to s is equal to sigma plus j omega. And what is sigma? So sigma is basically the complex, sigma is basically called the complex frequency. Sigma is called the complex frequency. So another important point is that if signal is absolutely integrable, so if signal is absolutely integrable, then we can put s is equal to j omega, and it will provide us the Fourier transform. So let us solve some problems. Suppose we have gt is equals to del t, then find out gf, that is the Fourier transform. So it is gf is equals to minus infinity to plus infinity gt e raised to the power minus j2 pi ft into dt. Sometimes it is very convenient to use omega, and sometimes it is very convenient to use f. And also f is basically 1 by t, so that is natural choice. If we just find out the frequency spectrum, so we can do solve in f domain also. So in gate they are asking mostly in f domain. So it is del t e raised to the power minus j2 pi ft into dt, and that is equals to 1. So the Fourier transform of this is 1. Let us discuss another example, that xt is equals to e raised to the power minus at into ut. Let us discuss this problem, and a is greater than 0. Let us discuss this problem. Find out xf, that is Fourier transform. So how to find out this? So xf is equals to minus infinity to plus infinity e raised to the power minus at into ut e raised to the power minus j2 pi ft into dt. Now it will be equals to 0 to infinity e raised to the power minus at into 1 into e raised to the power minus j2 pi ft into dt, and that is equals to 0 to infinity e raised to the power minus a plus j2 pi f into t dt, and that is equals to 1 divided by a plus j2 pi f. So this is xf. So xf is equals to 1 divided by a plus j2 pi f. So this is the Fourier transform. Xf is equal to 1 plus a plus j2 pi f. This is the Fourier transform of xt is equals to e raised to the power minus at into ut. Let us solve this problem. So we have a function called rect function. So we have a rect function that is represented by rect t, and between minus 1 to plus 1 by 2 the amplitude is 1, and for all other values it is 0. So rect t is equals to 1 from minus infinity 1 by 2 is less than or equal to 2 less than or equal to 1 by 2, and it is 0. For modulus of t it is 0. For modulus of t greater than 1 by 2 it is 0. So this is called the rectangular function. Now the general rectangular function, the generalized rectangular function is basically written as, let gt is the generalized rectangular function. It is written as a rect t divided by capital T. So if we draw the graph of this signal, then gt with respect to t is from minus t by 2 to plus t by 2. The amplitude is a. So from minus t by 2 to plus t by 2, the amplitude is a. So gt is equals to a when we have minus t by 2 is less than t less than plus t by 2, and it is equals to 0 when the magnitude of t is greater than t by 2. So when the magnitude of t is greater than t by 2, this is equals to 0. So this is a simply generalized form of rectangular function. So a is the amplitude, this rectangular pulse, a is amplitude, and t is the width. T is the width of the pulse. So our task is to find out the Fourier transform. So find out Fourier transform of this signal gt. So find out the Fourier transform. So let us solve this problem. So the Fourier transform is gf, and what is gf? So gf is written as minus infinity to plus infinity gt e raised to the power minus j2 pi ft into dt. And if we see that, we can find out from minus t by 2 to plus t by 2, this is a. So a e raised to the power minus j pi 2 pi ft into dt, and the solution is simply, we can simply solve this minus t by 2 to plus t by 2, and the solution of this is at. The solution is at sinc eft. And what is sinc ft? Sinc ft is equals to sine pi ft divided by pi ft. So sinc ft is equals to sine pi ft divided by pi ft. So this is sinc ft. This is sinc ft. So this gf is equals to at sinc ft. This gf is equal to at sinc ft, and also we can just we can plot this gf, the magnitude of gf, and the plot is like this form. So this is amplitude plot, amplitude spectrum. So the plot is like this form. So basically it follows the amplitude of the sinc pulse. This plot follows the amplitude of the sinc pulse. So here we have 80, and this is 0, this is 1 by t, this is 2 by t, this is minus 1 by t, this is minus 2 by t. And we can plot the sinc also, we can plot the sinc function also. So the plot of sinc function is we have sinc lambda, and that is the plot is like this. So this is decreasing, basically this is decreasing. So this is 0, this is 1.0, this is 2.0, this is 3.0, this is minus 1.0, this is minus 2.0, this is minus 3.0. So this is sinc lambda with respect to lambda. So this is the plot of sinc function. This is the plot of sinc function. So the maximum amplitude is 1, and it is basically the decreasing. It is basically the decreasing type. So this sinc function is basically the decreasing type. This is the major lobe, and these are smaller lobes are there. Very small lobes still existing, and it will make the bandwidth, theoretical bandwidth of this signal is infinite, but practically this is the main bandwidth occupied by this signal. Let us take this example. Let us take this example and find out the Fourier transform of the signal xt is equals to exponential at u of minus t, and it is for that value of this a is greater than 0. The value of a is greater than 0. So if we plot the signal, so first we can plot the signal xt with respect to t, then plot basically this is due to this ut, that signal will entirely exist in left hand side. There is no part in right hand side, because u minus t is equals to 1 when we have t less than 0, and it is equals to 0 when we have t greater than 0. So this is the graph of ut. So the graph of ut is like this. This is graph of ut, u minus t. This is graph of u minus t. So let us see that if we increase the value of t in negative side, so what will happen at when we have t is equals to minus infinity, it will 0, and it is just like this graph. It is just like this graph. At t is equals to 0, the value is 1. At t is equals to 0, the value is 1, and it is just decreasing. It is just decreasing. So this graph, if we see that graph, it is basically that it is slowly rising from minus infinity, and it will achieve the maximum value. It will achieve the maximum value, that is 1. So this is xt graph, that is exponential at u minus t, and let us find out the Fourier transform. So Fourier transform xf is minus infinity to plus infinity xt e raised to the power minus j 2 pi ft into dt. So it is xf is equals to minus infinity to plus infinity xt e raised to the power minus j 2 pi ft into dt. So xf is from minus infinity to 0, it is exponential at multiplied by 1 multiplied by e raised to the power minus j 2 pi ft into dt. And so from minus infinity to 0, this is u minus t is 1. That's why we have written in this way. So it is exponential at minus j 2 pi ft into dt. So we can just if we solve this, so what we will get? We will get 1 divided by a minus j 2 pi f. So this is xf. So xf is 1 divided by a minus j 2 pi f. So this is xf. Now let us see some properties of the Z transform. Let us see some properties of the Z transform. Properties of Z transform. So the first property is linearity property. The first property is linearity property. So according to, and also this linearity property is also called the superposition. It is also called the superposition property. It is also called the superposition property. So let G1t has Fourier transform G1f and G2t has Fourier transform G2f. Then if we get the combined signal, that is A G1t plus B G2t, the Fourier transform will be A G1f plus B G2f. So this property is called the linearity property. This property is called the linearity property, and basically if we are taking the combination of this signal according to this property, if we taking the combination of this signal, then we have to get the combined signal of this. And this A and B are basically constants. A and B are basically constants. These are constant multiplication. Now we can see some examples related to the linearity property. So let us solve some problems related to linearity property. So first problem is combination of exponential pulses. Combination of exponential pulses. So consider a double exponential pulse. Consider a double exponential pulse. Consider a double exponential pulse GT. So GT is written as exponential minus AT when we have t greater than 0. It is equals to 1 when we have t is equals to 0, and it is equals to exponential AT when t has value less than 0. So this is GT. Now GT can be written in this form, that is exponential minus a modulus of t. This can be written in this form. Now our task is to find out. So we need to find out Fourier transform of GT, that is equals to GF. Find out the Fourier transform of GT. Find out the Fourier transform of GT. So let us solve this problem. So if we draw the signal GT, so GT is exponential minus a modulus of t. So if we plot the GT, then what we will get? We will get, if we plot the GT, then the plot of GT is like this. This is the plot of GT. So here we are getting a value of minus 1 divided by a, and here we are getting a value of 1 divided by a, and this is 0. So this is the plot of GT, and this point is 1. At t is equals to 0, we have 1. So basically this figure is called double exponential pulse. So this figure is called the double exponential. This figure is called the double exponential pulse. And if we see the symmetry, then we can say that it is symmetric. It is symmetric signal. It is symmetric signal. It is showing the even symmetry. It is showing the even symmetry. It is showing the even symmetry. We can see that this signal is symmetric along that y-axis. Along that y-axis, the signal is symmetric. Now we can find out the Fourier transform of this. So Fourier transform of this is exponential minus a mod t. The Fourier transform is equals to 2 divided by a square plus 2 pi f whole square, and we can prove that. So let us prove this problem. So we have gt, that is equals to exponential minus a modulus of t. So let us prove this. So it can be written as exponential minus at ut for t greater than 0, and it can be written as exponential at u of minus t when t less than 0. So let us solve this problem. So gf is minus infinity to plus infinity gt e raised to the power minus j 2 pi ft into dt. So if we solve this problem, then we can say that gt is a combination of two signals, g1t plus g2t. So from minus infinity to, so if we find out the gf, then from minus infinity to 0, basically this gt is we can write it as exponential at into 1 into e raised to the power minus g2 pi ft into dt, plus from 0 to infinity we can written as exponential minus at into 1 into e raised to the power minus jt phi 2 pi ft into dt. So this is gf. So this is basically the linear combination of gt is basically the linear combination of these two signals. So that is property is simply linearity property. So what is the value of gf? So if we solve this expression, then what we will get? We will get the solution of this expression is if we solve this expression, then we will get 1 divided by a plus j 2 pi f. If we solve this expression, what we will get? We will get 1 divided by a 1 divided by a plus j 2 pi f, and if we solve this expression, what we will get? 1 divided by a minus j 2 pi f. So this gf is equals to the solution is 2a divided by a square plus 4 pi square f square. Now what we can find out? We can find out the amplitude. We can find out the amplitude of this. So what is the amplitude? So that modulus of gf. So that modulus of gf. The modulus of gf is 2a divided by a square plus 4 pi square f square. So this is the modulus of gf. So the gt is equals to exponential minus a modulus of t. The Fourier transform is 2a divided by a square plus 2 pi f whole square. So we can say that that expression shows that it is an that gf, that's the Fourier transform of this gt, that is gf. It is an even function of f. It is an even function of f, because gt is real. Because gt is real signal. Since gt is real signal, the Fourier transform, the amplitude spectrum, basically that the real function of f. If we see the amplitude spectrum, we can say that it is real function of f. It is an real function, even function of f. It is an even function of f. Even function of frequency f. So we have proved that relation that we have studied in previous lecture. Now Again, we can see one example related to this linearity property. So before that, we have a signal that is called signum t. So what is the plot of signum t with respect to t? If we plot the signum t, then signum t is +1 when we have t greater than 0. It is -1 when we have t less than 0. So this signum t is equals to +1 -1. So +1 when we have t greater than 0, -1 when we have t less than 0. So this is signum t, and it is discontinuous at t is equals to 0. The signum t is discontinuous at t is equals to 0. So we have gt. Let us define gt. There is signal, there is double exponential signal gt, and this signal is defined in this way. So this is gt. So gt is equals to exponential minus at when we have t greater than 0, and it is equals to 0 when we have t is equals to 0, and it is equals to exponential at when we have t less than 0. So it is equals to minus. Here we have minus, so it is equal to minus exponential at when t less than 0. So this gt can be written in this form of signum. So gt can be written in the form of signum function. So how we can write, since it is +1 here, it is +1 exponential minus at when we have t greater than 0. So we can write it as exponential. So we can write it as exponential minus at signum t when we have t greater than 0, and it is also, we can write it as exponential at into signum t when we have t. So it is written as basically exponential minus at. Better to write in this way. So yes, this is not correct. So better to write in this way. So we can summarize these two. So better to use the mode. So it is minus a modulus of t and multiplied by signum t. This is better way to write gt. Now if we just carefully observe this relation, then signum t for t greater than 0, if we just write in this proper way, so gt is exponential minus a modulus of t into signum t. So let us see that expression. So for t greater than 0, signum t is equals to +1. So what gt will become? So gt will become exponential minus at. And for t less than 0, this gt will become because signum t for t less than 0, signum t is equals to -1, so this gt will become exponential at. So our relation is proved. That's this is the definition of gt, and that is t is equals to 0, it is equals to 0. Now so this is our gt. We can find out the Fourier transform. So to find out the Fourier transform, gt can be represented as a sum of two signals. So one signal is and here minus sign is there. So gt can be represented as g1t plus g2t, and it is gt is basically the linear combination of g1t and g2t. So g1t is exponential minus at, and g2t is exponential minus exponential at. So these two signals are there. Now gf is basically g1f plus g2f. So if we solve this, what we will find out? We will find out that we have g1f, that is 1 divided by a j pi plus 2 pi f. Then we have g2f, that is 1 divided by a minus j 2 pi f. Now further, if we further solve this, here we have this minus. So if we solve this, so that what we will get? We will get minus j 4 pi f divided by a square plus 2 pi f whole square. So this is gf. So let us write gf. So gf is equals to minus j 4 pi f. gf is equals to minus j 4 pi f divided by a square plus 2 pi f whole square. So what is the conclusion here? That since gt, if we see the graph of gt, so the graph of gt is like this. So this is an odd symmetry. It shows odd symmetry. So what we are getting here, for odd symmetric signal, the Fourier transform for this odd symmetric signal, the Fourier transform is purely imaginary. The Fourier transform is purely imaginary function of frequency f. So it is purely imaginary, and also it is odd. It is purely imaginary because g minus t is equals to minus gt. Since g minus t is equals to minus gt, since it is odd, it is showing odd symmetry. So the Fourier transform of this is purely imaginary and odd. So the Fourier transform of this is purely imaginary and odd. So the second property is called the dilation property. So if gt has Fourier transform, according to this property, if gt has Fourier transform gf, then gat has Fourier transform is equals to 1 divided by modulus of a gf by a. So this property is called the dilation property, and if a is equals to 1, then gt is 1 divided by modulus of 1 gf. So gt is equals to so if a is equals to minus 1, let us take a is equals to minus 1, then that will be better example. So if a is equals to minus 1, then it is equals to minus 1, then it is equals to minus f. So gt is equals to minus gf. So gt is equals g minus t is equals to, here g minus t is equals to g minus f. So gt has Fourier transform gf, then g minus t should be the Fourier transform of g minus f. So g minus t has Fourier transform g minus f. This is called the dilation property. So some important results are there in this dilation properties. Let us discuss these points. Here a is the dilation factor. So here a is the dilation factor, and one of the important thing is that about a is that a is a true number. So to prove this property, let us prove this property. So to prove this property, we note that if we have GAT, then the Fourier transform of GAT is equals to minus infinity to plus infinity GAT exponential minus j 2 pi ft into dt. Now let us set tau is equals to 80. Set tau is equals to 80. So there are two cases that can arise. There are two cases that can arise depending on whether dilation factor A is positive or negative, depending on whether the dilation factor is positive or negative, So let us discuss first. So if A is greater than 0, we get Fourier transform of AT is equals to so if A is greater than 0 and setting tau is equals to 80, so what we will get, it is equals to 1 divided by A minus infinity to plus infinity g tau exponential minus j 2 pi f divided by A. The frequency will change to f divided by A multiplied by tau d tau. So just we have taken AT is equals to tau. So dt will change to d tau divided by A. So here we are getting the factor 1 by A that we have put outside the integral. We have replaced AT with tau, and here we have t is replaced with tau by A. So here that t is also replaced with tau by A. So what we are getting here, we are getting that the Fourier transform of GAT, is equals to 1 divided by A GF by A. So the Fourier transform of GAT is equals to 1 divided by A GF by A. And on the other hand, if A is less than 0, then the limits of integration are interchanged so that we have the multiplying factor, that is equals to minus 1 divided by A, or equivalently 1 divided by modulus of A. So what we can find out that GAT, if we find out GAT, then it is basically, if we say that what is GAT, then it is basically that compressed by factor A, and GF by A, it means it is expanded by factor A, and all these two conditions are true when we have 0 is less than A less than 1, when we have 0 is less than A less than 1. So the dilation The dilation rule states that the compression of signal gt in time domain is equivalent to the expansion of its Fourier transform is equal to the expansion of its Fourier transform GF in frequency domain by the same factor or vice versa, by the same factor or vice versa. So we have another property that is called conjugation rule. So we have another property that is called conjugation rule. So let GT has Fourier transform GF. Let GT has Fourier transform of GS. Then for a complex valued time function GT, we have G conjugate T is equal to G conjugate F. So G conjugate T is equal to G conjugate F. So where the star denotes the complex conjugate operation, denotes the complex conjugate operation. So let us prove this property. So we have GT, that is the Fourier transform, is equal to GF. So basically GF is the inverse Fourier transform. GT is inverse Fourier transform of GT. So GT is written as minus infinity to plus infinity GF exponential J2 pi ft into df. This is the inverse Fourier transform. So this is inverse Fourier transform of GF is GT. So this is the formula for getting the GT back from GF. By doing this formula, we are performing the inverse Fourier transform. So if we take G conjugate T if we take conjugate on both sides, then what we will get? We will get minus infinity to plus infinity G conjugate F exponential minus J2 pi ft into df. Now what we are getting here, if we and also this conjugate will make it plus. Now if we do one thing, if we replace f with minus f, then what we will get? We will get G conjugate T is equals to minus infinity to plus infinity G conjugate minus f exponential minus J2 pi ft into 2 pi ft into df. Now what is happening here, we can just see that this is nothing but the Fourier transform. So G conjugate T is equals to this. So basically we can say that the Fourier transform of G conjugate T is equals to G conjugate minus F. So if we just carefully see the relation, then this relation is observed that the Fourier transform of G conjugate T is nothing but it is equals to G conjugate minus F. So the property is, if GT has Fourier transform GF, if GT has Fourier transform GF, if GT has Fourier transform GF, then G conjugate T has Fourier transform G conjugate minus F. So this property is called the this rule is called the conjugation rule. This rule is called the conjugation rule. This rule is called the conjugation rule. So let us try another property, that is this property is very important, and this property is called the duality property. This property is called the duality property. So according to this property, if GT has Fourier transform, if GT has Fourier transform GF, if GT has Fourier transform GF, then capital G small t has means capital GT has Fourier transform G minus F. So we can just prove this property. We can just prove this property. So let us prove this property. So GT is this Fourier transform of GT is GF. So GT is equals to minus infinity to plus infinity GF exponential J 2 pi ft into df. This is the expression for inverse Fourier transform. This is the expression for inverse Fourier transform. Now if we just take G minus t, then it is equals to minus infinity to plus infinity GF exponential minus J 2 pi ft into df. Now we are just going to replace t with f. We are going to replace t with f. So what we will get here, we will get G minus f is equals to minus infinity to plus infinity GT exponential minus J 2 pi ft into dt. So this G minus f is, if we just observe that, then this is the Fourier transform of GT. This is the Fourier transform of GT. So let us take an example. So we know that A rect t by t has Fourier transform AT sinc ft. So this A rect t by t has Fourier transform A sinc ft. Now if we find out the Fourier transform of this signal, that is if we find out the Fourier transform of AT sinc t capital T, then it should be equals to A rect minus f divided by capital T, and that is equals to A rect f divided by capital T, because rect is an even function. So AT sinc T capital T has the Fourier transform A rect f divided by capital T. So so a very important conclusion is that A sinc T small t has the Fourier transform that Fourier transform is equals to A divided by capital T rect T divided by capital T. So this is your rect function. This is basically f. So this is f. Here we have minus t by 2. Here we have plus t by 2. And this is amplitude is a divided by t. The amplitude is a divided by t. So basically if we observe that, and then the sinc function is, this is the sinc function, this is the sinc function, this is the sinc function. So this is a sinc capital T small t, this is the sinc function, this is 0, and this is 1 divided by t, this is 2 divided by t, and this is minus 1 divided by t, this is minus 2 divided by t. So if we carefully observe that, so this a sinc capital T small t, the Fourier transform is this signal, and if we just carefully observe that, so it is noted that the Fourier transform of sinc function, that the Fourier transform of sinc pulse. So this is sinc pulse, this is sinc pulse. The Fourier transform of sinc pulse is 0 for modulus of f greater than t by 2, modulus of f greater than t by 2. So it means that, so note also that the sinc pulse, itself is, the sinc pulse itself is only asymptotically, is itself, sinc pulse is only asymptotically limited in time, in the sense that it approaches 0. So limited in time in this sense that it approaches to 0, in the sense that it approaches to 0, time. So basically it will approach to 0 when t tends to infinity. So we can see that this is decreasing, so we have when t is equals to t tends to infinity, that sync will approach to 0. So we can say that this property, so basically this because this is bounded, you can say that, so this will make sinc function an energy signal. So what we have observed, that the sinc function is an energy signal because it is bounded basically, So sinc function is an energy signal, so it is an energy signal. This is very important property of sinc function.